We are the Lethbridge High School iGEM team from Lethbridge, Alberta. Alberta is known for its agriculture industry, a leading force for the provincial and national economy. Alberta's agricultural exports were valued at over $16.1 billion in 2022 and $17.9 billion in 2023, which shows this sector's contribution to the economy. Our province has a diverse crop production industry, including oats, barley, canola, and pulses, the most common. Alberta has about 680,000 hectares of irrigated land, making it Canada's largest irrigated land area. Water is used most in Alberta for agriculture irrigation, accounting for 60 to 65% of all the water consumed in Alberta. In most of southern Alberta, there are low amounts of rain and moisture to support crops. To grow crops, farmers require large amounts of water. Over the past few years, Alberta has gone through extreme weather conditions affecting crop growth. Overwhelming heat has shortened growing seasons, lowered crop production, and increased the amount of water required to sustain plant life. Alberta manages water resources through reservoirs, canals, and pipelines, alongside modern irrigation systems like center pivot irrigation to reduce waste and improve crop yields. Soil moisture sensors prevent over-irrigation by providing real-time data, while drought-tolerant crops, mulching, and cover cropping help retain soil moisture and reduce water needs. Additionally, genetically engineered seeds are being developed to withstand changing environmental conditions, though this approach is costly and time-consuming. Alberta's current water management strategies help conserve and distribute water, but they are not enough to combat increasing drought conditions. Reservoirs, irrigation systems, and soil moisture sensors rely on available water, which is becoming more scarce. Genetically engineered seeds offer a long-term solution, but they are costly, time-consuming to develop, and may not adapt quickly enough to Alberta's changing climate. Our project is called RhizoRetention. We want to engineer a rhizobacterium to help plants retain more water for longer periods to reduce the amount of water they use. The rhizobacteria will produce a compound to help the plants conserve water. We have picked abscisic acid, or ABA, as our hormone to prevent water loss and increase retention. ABA triggers the plant to close its stoma, reducing water loss through transpiration. Two types of bacteria we have thought of are Pseudomonas fluorescens and Bacillus subtilis. ABA is synthesized from carotenoid precursors through a sequence of enzymic reactions. Key enzymes like ZEP and NCED play vital roles in this pathway. Signaling pathways are mediated by ABA receptors that inhibit protein phosphates, activating kinases, and triggering stress response gene expression. After the genes are cloned, we will use the Gibson assembly method to insert the biosynthetic genes into plasmids or integrate them into the bacterial genome.
To test our idea, we would grow canola plants, oat plants, and barley plants. Plants of each type will be grown in a controlled environment. To help with this, we want to work with the Department of Biological Sciences at the University of Lethbridge, and hopefully you'll be able to use their greenhouse. Plants of each type will be given our rhizobacteria serum. After the plants sprout leaves, we will use a pressure chamber and other devices to measure the amounts of water in each. We envision our formula in liquid form. Farmers will be able to spray it over crops. The solution will produce ABA, and the ABA would be absorbed through soil uptake into the roots of the plant. Once in the plant, ABA will begin to perform its various roles.
Biosafety concerns are also a huge part of our project in thinking about how we want to do it. One of ours, firstly, is what is our guarantee that the bacteria won't run into water supplies? Well, we can use containment methods such as pipes at the ends of fields to catch any runoff, as well as self-deploying bacterial nets. Secondly, will the bacteria die out normally after a certain period of time? If not, how do we remove them? Each bacteria will be naturally installed with a kill switch and make the bacteria self-destruct after a certain amount of time or when it hits a certain stimulus. Lastly, will this modified bacteria harm the plant in any way? No, it will not be absorbed into the plant, it will only be on the surface, it will not be consumed by humans, so therefore there is no concern of it competing with naturally occurring bacteria.
Will stomatoclosure affect other life processes of the plant? We will create different solutions of our product, each containing rhizobacteria that will secrete specific concentrations of ABA. These concentrations will be tailored to different seasons and plant types. The rhizobacteria in our product will respond to certain environmental conditions such as temperature. They will only secrete ABA when the plant needs it based on these environmental cues. This targeted approach ensures that our product does not interrupt routine plant processes. Somatocloser is a natural response to environmental conditions, and our product aims to enhance this process when necessary.
Stakeholders and collaborators also play a very important role in our project, and listed are the individuals that we believe will help create our prototype and educate us on farming practices.
Helping plants hold more water to reduce water usage in farming directly supports the UN sustainability goals of zero hunger, clean water and sanitation, and responsible consumption and production. Our next steps include contacting the University of Lethbridge Department of Biological Sciences and beginning the process of growing the canola, oat, and barley plants. We will also begin our work with rhizobacteria, making pathways for ABA. Additionally, we will start communication with local farmers to find ways to make our project better. Our project focuses on plant water retention using rhizobacteria to produce abscisic acid. This substance boosts water retention and drought tolerance in plants. By applying these bacteria to plant roots, we can enhance the resilience in dry conditions, ultimately supporting better growth and productivity. This offers a sustainable way to help crops thrive in water-scarce areas. Overall, this will help farmers during drought periods so that plants don't need to take up as much water, resulting in longer growing seasons and more crop yields.